In this sequence, we would like to look at tensors as data structure. We would like to learn what tensors are, how they can be manipulated, and also a bit how they can be implemented in Python. For our purposes, a tensor can be defined as a multidimensional array, typically of numbers. Please note that this is a computer science definition that focuses only on the data structure. If you're studying other areas, such as mathematics, physics, or mechanics, things are a bit more complicated. There would also be some structure and semantics to the definition of what a tensor really is. But this is not relevant for this course. Tensors are a core data structure for machine learning, and specifically also for deep learning. In fact, Google's TensorFlow, which is one of the most prominent deep learning packages, has tensor even in its name. We can define the rank of a tensor to denote the number of dimensions. For example, a vector would have rank 1 and a matrix would have rank 2. Now, this is different from the definition of matrix rank in linear algebra. In linear algebra, when we're looking at a matrix and think about matrix rank, it's related to the maximum number of linearly independent column vectors. But this definition simply looks at how many dimensions we have in the definition of the data structure, and for a matrix this will always be 2, and for a vector always be 1. It's also different from the number of entries in a matrix or a vector, which is also sometimes called the dimension. So, for example, a vector consisting of 7 elements would be called a 7-dimensional vector. However, if you think of the vector as a tensor and want to know what's its tensor rank, then the rank would be 1. A dimension is often called an axis. If you would like to know the tensor rank, you can use the Python command .ndim. Scalars. So scalars are 0D tensors. For example, a, b, x element of R would be scalar numbers. Vectors are 1D tensors or tensors of rank 1. For example, a vector x element of R4, we would call this a 4-dimensional vector, but we would call this a tensor of rank 1 or a tensor that has 1 dimension. Or we could also say it's a tensor with 1 axis. As you can already guess, this terminology is slightly confusing and not very precise. However, you will see it used in practice by many different people in slightly many different forms. So that's just something to deal with. Here's a short program that uses the command ndim. First line, this is in almost every scientific computing, machine learning software in Python. The first line you import numpy as np. And this name np is universal. Almost everybody uses np. So first line, we define a vector as an array of numbers, and the entries of the vector are 7, 3, 5, 11. And in the next line, we print out this vector, and then we ask for its dimension. All right, let's look at that in Python. So this is Google Colab, and Google Colab is a great way to just start implementing in Python without doing a lot of installation on your computer. So basically you just need to go to the web page, log in, and you can immediately start programming. So this program is similar to what I had in the slides, and first line you import numpy as MP, then you define x as a vector. This is a numpy array with 4 elements, 4 entries, 3, 5, 9, and 2. And then we're going to print out the vector, and we're going to ask for its dimension in the sense of tensor rank. So we'll start this program, and then we'll see that the entries are 3, 5, 9, 2, as expected, and the tensor rank is 1, not 4, according to their 4 entries in the vector. So just to verify that, we're going to add maybe more numbers here, and then we'll start this again and see that the tensor rank stays the same. All right, so we can also try print length of x and start this again. So now we see that the tensor rank is 1, but the number of entries of the vector, or the dimensions of the vector, are 6. So matrices are 2D tensors. Matrices have 2 axes, rows, and columns. For example, what we see here is a matrix A that is an element of R2 cross 3. That means we have 2 rows and 3 columns. Again, looking at this code here, this is how we would define a matrix in Python. So that is a matrix as an array, numpy array, and then you can print the matrix. Then this means print its elements, and then again we can print out the tensor rank. Now, most of the time we will actually be dealing with higher dimensional tensors. For example, images by themselves are 3D tensors. If we have given an image I, then I is has typically a width W, a height H, and it will have 3 color channels: red, green, and blue. For example, an image could be 1000 times 1000 times 3. Even though in deep learning the images are typically a bit smaller, because otherwise the deep learning algorithms run out of memory. So while your state-of-the-art camera and iPhone will be able to take pictures, will able to take images that have a much larger size, 4 megapixels, 16 megapixels, 20 megapixels, the images that are processed in deep learning will be quite a bit smaller, maybe more like 512 square. In convolutional neural networks, networks that are specially suitable to process images, we will discuss them later, then we will have images with many channels C. So while only in the beginning the input image will have 3 channels, red, green, and blue, then as the images are processed by the neural network, the number of channels will typically increase quite a lot. So it will not be uncommon to have tensors that will have width and height that's maybe a bit smaller, but the number of channels could be 512 or 1024. So that means we will have a lot of these tensors of the form with height times number of channels, where this can be up to a few thousand. In deep learning, we generally manipulate 0D to 5D tensors. Where do these 5D tensors come from? Well, we need to consider that generally we not only process one element of data at a time, like one image at a time, we will do some batch processing, or batch is a small set or a small sequence of, let's say, images. So let's say we have a small sequence of images and the batch size is n. That means we have n images. Then this gives us already a 4D tensor. So this set sequence of images ij will be an element of R with height times channel, and then what is the index of this image in the batch. Now, these tensor axes can be ordered arbitrarily. Probably most dominant in deep learning software at the moment is the convention to have the index inside the batch as the first one. So you would have something that's more this sequence of images is an element of this tensor R to the power of n cross width cross height cross number of channels. Now, this type of notation to always write R to the power of something is a bit complicated. So a simpler notation is to write something like, okay, maybe we have an image, and this is a tensor of rank 3, and the axes are width, height, and channels. Also, you will see something in the PyTorch help, or in the PyTorch that reads something like, okay, this type of function or layer has an input size of this. That means the input is expected to be a rank 4 tensor that has the following axis. This is the index of the element within the batch. These are the number of input channels. This is height and width. And then out you get another tensor. That again is the index. Then you have the number of output channels, the height and width of the output tensor. So as this is taken from, I think, the definition of a convolutional layer. So what you see here is that this building block of a network that we'll discuss later will take a tensor as input, or actually a set of tensors as input, and then give you a set of tensors as output, but the height, width, and the number of channels will be different. But the number of tensors that you get will be the same. So how do we get to 5D tensors? Well, if we're processing video, then we not only have single images, but each element will be a sequence of images. So we will have samples. This is the index of the video in the sequence of videos. Then for each video, we will have multiple frames, that each frame is one image. And then for each of the image, we will have height, width, and the channels. All right. So you can imagine that if you're thinking about processing a larger number of videos, that this could be quite a lot of memory. So let's say you're idealistic, you want to start out, you want to process 1,000 samples at a time. Each of the videos will have 10,000 frames, and height and width will each be 1,000, and channels in the beginning will be 3. This will still be a prohibitively large number. So here are some Python commands to look at. This gives some random tensor. In this case, this is a tensor of rank 3. And what you see here are, there will be 3 axes. and then like how big is each of these axis dimensions. So we have a tensor that has size 3 times 2 times 4. That means there will be 3 times 2 times 4 elements in this tensor. And then these commands here that you see below can tell you something about this tensor. So that's what we had, is the rank of the tensor is expected to be 3. Then a dot shape, that gives you the dimensions along each axis. And then a dot d type is the data type of the tensor. So you can just copy this code and type it in yourself to see what it does. Next, we want to think about manipulating tensors. This is somewhat beyond the scope of this class. I will just drop a few hints. So, importing NumPy as MP, discussed before, and here I generate a random rank 3 tensor that has 300 times 200 times 100 elements. It's important to familiarize yourself with the slice notation. For example, this tensor B now will be a subtensor of this tensor A, and these are ways to basically access the different axes. So what we'll do is, instead of having all 300 elements here, it's basically defining a slice through the tensor, we will only have 20 to 50, and then in these other two axes we'll take all elements. And similarly, there are all these other tricks like 10 colon means, okay, we'll take it to the end. This again means we take all elements, and then some notation like minus 20 means we're counting from the end backwards. All right, this is not enough to really understand what's going on. The goal here for you is to take this code, copy it, and play around with it, and read some documentation or some tutorial online. All right, so this will reveal something about the new tensors by printing out their shape. Okay, so this is another example. We'll define here a rank 2 tensor. This is a matrix. Then we'll print out the matrix. Then we'll create a vector, and we would like to implement the standard matrix vector multiplication. This is basic linear algebra in Python, and so the matrix vector multiplication can be computed by this dot command. Now this dot command is heavily overloaded. You can use it for matrix vector multiplication. You can use it to compute the dot product and some other things. So again, just go and look up the documentation or some tutorial online. It's important to note that we will do a lot of element-wise manipulation. So, for example, if you would like to compute the maximum here, as you see here, maximum of A and 2, this is an element-wise maximum. So what this would do is it would go through the whole tensor, in this case matrix A, and for every element it will take the maximum of the element and 2. All right. Another very important concept is broadcasting. For example, let's look at the element-wise addition of two tensors. Conventional wisdom and mathematics would say that two tensors need to have compatible size. However, broadcasting loosens that restriction, and it lets you kind of combine two tensors even if they have different size. So there will be a smaller and a bigger tensor, and what broadcasting does is it will replicate the data of the smaller tensor to make it compatible with the bigger tensor. So So basically the broadcast axis will be added to the smaller tensor. So the smaller tensor will have fewer axes, will be added to the smaller tensor to match the larger tensor, and then the smaller tensor will be repeated alongside the new axis. So in general, the larger tensor will have a bunch of leading axes here, and then it will have the axes that are in common with the smaller tensors, n, n plus 1, and so on to m. This is the size of the smaller tensor. And so what will happen is that this axis a, b, c up to n minus 1 will be added to the smaller tensor, and then the tensor will be replicated along these axes. Here's a broadcasting example where we have a matrix and then we have a vector, and we can add a matrix to a vector using this wonderful tool of broadcasting. So broadcasting is a fairly important concept that you also have to familiarize yourself with. Reshaping tensors is also very important. So you can, for example, have this matrix, and then you can reshape it to give you matrices of different sizes, and you can also transpose a matrix. So we'll leave it at that, and I'm just quickly going to switch to Google Colab again to show some of these commands in action. Okay, let's look at this code in Python. So here is just a demonstration what a.ndim does if A is a matrix. So as expected, that gives out 2. And so here you can also see how does this matrix look like printed out. Next, we'll generate a tensor A with this command that fills it with random values. Let's look at the result. So you can notice that tensors become pretty big pretty quickly. So even though this is only a 3 times 2 times 4 tensor, there are quite a lot of values. So just typing this in within the code directly would already take quite a bit of space. So a.ndim, as expected, this is a rank 3 tensor, gives us 3, and a.shape gives us the dimensions along each axis, so 3, 2, 4, and that's the same as what has been requested above here. And then we have float 64 is a.dtype is the data type. All right. So changing that to 117 and executing again, we'll see that indeed 117 is reflected here with a.shape. So some comments on the slice example. What we see here is obviously there was a mistake in the slides when I talked about them. So this should be 20:50 to use this slice notation. Now this tensor A is way too big to print it out, so we can only print out the shape of B and C. Let's see what that does. So the shape of B that is constructed with this notation here is now 30 times 200 times 100, and C that's constructed with this notation here is 290 times 200 times 60. This is the demonstration of matrix vector multiplication. So we have A is a matrix, and we can see that these are indeed the values that we entered in the code. And then I multiply this matrix A with this vector X, and then we get this result. So anyway, we can see if this is true or not. So we can see that the first value, well, I guess you just have some time to check if that's really true, or maybe you can experiment with the values yourself. Let's just go to this one, So the matrix 9, 9, 9, minus 4, 5, 0, these are the entries. And now we do an element-wise maximum. So wherever we have a value that's smaller than 2, we will replace it with 2. So what we'll expect is 9, 9, 9, 2, 5, 2. And that's what we see below, 9, 9, 9, 2, 5, 2. All values smaller than 2 have been replaced by 2.